Welcome to Spring LIB.
We are given these two half reactions that occur within a galvanic cell, and we ultimately want to determine what the value is for a weak acid, HA, that has been dissociated to produce H plus ions. And when we talk about Ka, then we are dissociating the weak acid, HA, reversibly into aqueous H plus ions plus aqueous A minus ions. And these are all aqueous species, so the value for the equilibrium of this dissociation is equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA. So once we have these three species concentrations, we can plug them into this ratio in order to determine Ka. We can use the Nernst equation in order to find the concentration of H plus ions that we have, and based on the fact that this is a one-to-one stoichiometry, that would also equal the concentration of A minus ions that we have. So we would square the concentration of H plus ions for the numerator, and for the denominator, we are told that we initially have 1.00 molars of this weak acid. So the first thing that we need to do is find the concentration of H plus ions, and we need to use a Nernst equation to do that. And part of the Nernst equation is solving for the standard cell potential. We know that this is a galvanic cell, so we have to rearrange the two half reactions in such a way that gives us a positive value for the cell potential. And we also know that one of these reactions has to be reversed to undergo oxidation so that we can cancel out the electrons. When we compare the two given values for the standard reduction potentials, we see that 0 is greater than negative 0.440. So that means H plus will be reduced to form hydrogen gas, while we reverse the first reaction so that iron will be oxidized to Fe2 plus. And when we do that, we also have to reverse the sign of the standard reduction potential to be 0.440. When we rearrange the equations that way, we see that 2 electrons cancel out on either side. We are left with an overall cell reaction of solid iron plus 2H plus aqueous going to Fe2 plus aqueous plus hydrogen gas. And now we can add those two potentials together to get the overall standard cell potential. And that comes out to 0.440 volts. And now we plug this into the Nernst equation, where the non-standard cell potential is equal to the standard cell potential that we just solved for, minus 0.0591 over N times the log of Q. We can develop an expression for the reaction quotient Q based on the aqueous species concentrations of our overall reaction. We see that that corresponds to Fe2 plus, that concentration on the numerator, divided by, on the denominator, the concentration of H plus squared. So Q is equal to the concentration of Fe2 plus, which we are given in the problem statement, divided by the concentration of H plus, which is what we are solving for, squared. And now we can plug in what we know into the Nernst equation to solve for that concentration of H plus. We are told that the non-standard cell potential is 0.333 volts. This equals the standard cell potential, which we calculated to be 0.440 volts minus 0.0591 over N. We canceled out 2 electrons on either side of the equation, so N is equal to 2, times the log of Q, where we use that expression for Q that we just developed, and we are told that the concentration of Fe2 plus an iron compartment of this galvanic cell is 1.00 times 10 to the power of -3 molar. We divide that by the concentration of H plus ions squared. Now we can rearrange the Nernst equation to isolate and solve for that concentration of H plus. We subtract over this term to the left side of the equation, and then we divide that negative ratio by the result, take 10 to the power of that result to get rid of the log, and then divide and take the square root to find the concentration of H plus ions. And we should find that that comes out to about 4.89 times 10 to the power of -4 molar. And now we said that once we had that value for H plus, that would also correspond to the concentration of A minus due to that one-to-one stoichiometry. And again, we are told that HA is equal to 1.00 molar. So really, that means that Ka is just equal to that concentration of H plus ions squared. So to find Ka, we just take that value of the concentration of H plus to be 4.89 times 10 to the -4th molar, and we square that value, and that comes out to about 2.39 times 10 to the -7 molar.